So now let us see different theorems related to the chord of a circle. So in this case, in this video, we'll be seeing two important theorems related to angles subtended by a chord at a point. Angle subtended by a chord at a point. In this topic, the first theorem says that equal chords of a circle subtend equal angles at the center. Right. The first theorem says that the equal chords of a circle subtend equal angles at the center. That is, say, this is my circle, this is my center. Say I have one chord here like this, and I have another chord here like this. This is AB, this is PQ, and it is given that the length of chord AB is equal to PQ. So if I'll join point B with the center, point A with the center, I got an angle theta. Say this angle is theta. Similarly, if I'll join P with center and Q with center and say this angle is phi. So as per this theorem, theta will be equal to phi, given that AB is equal to PQ. Second theorem is the converse of the first theorem. That is, if the angles subtended by the chords of a circle at the center are equal, then the chords are equal in length, right? If the angles subtended by the chords of a circle at the center are equal, then the chords are equal in length. This is the converse of the first theorem, right? So let me explain the second theorem. Second theorem says that if I have a circle, say this is the center, this is my one chord, this is my another chord, say this is AB, this is PQ. Let me join A and B with the center and P and Q with the center. Say this is theta, this is phi. If it is given that theta is equal to phi, then this implies AB is equal to PQ. This is what the second theorem says. Now let us see the proof of both the theorems. Let us start with the first theorem. As per the first theorem, let us consider a circle. This is my center, this is my one chord, this is my another chord, AB, PQ. Let me join that, both of them with the centers. Now, it is given that AB is equal to PQ, and we need to prove that, say this point is O, angle AOB is equal to angle POQ. Now, let us see how to prove that. Consider triangles AOB and triangle POQ. This triangle AOB and POQ. Let us consider both the triangles. Can I say that AO is equal to OQ? Why? Because both are radius of the circles. Similarly, can I say that BO is equal to OP? Why? Because again both are radius of the given circle, and it is given that AB is equal to PQ, right? So can I say that triangle AOB is congruent to triangle POQ by SSS congruency criteria? So now since it is congruent, therefore I can say angle AOB is equal to angle POQ CPCT, congruent corresponding parts of congruent triangle, and this is how we prove our first theorem. Now let us go to the second theorem. That is the converse of the first theorem. As per the second theorem, It says that if I have a circle and if I have two chords, say AB and PQ, if I join, this is my center O, let us join AO, BO, PO and OQ. See this angle, now it is given that angle AOB is equal to angle POQ. This is given, right? Also, I know that AO is equal to OQ, Y radius, and also BO is equal to OP, again the radius. So can I say that triangle AOB is again congruent to triangle POQ? But in this congruency criteria will change. Both triangles are congruent because of SAS congruence criteria. Now since they are congruent, therefore AB is equal to PQ, corresponding parts of congruent triangles. Hence this is the proof of the converse of the first theorem, that if this angle is equal to this angle, then the length of the chords will be equal. So I hope both the theorems are pretty clear, and this will help in solving questions related to chords of the circles.